In this video, we look at internal energy changes as they specifically relate to heat. We'll start first with a slide that just shows some equations associated with something called the equal partition theorem. For those of you who took PChem in the first semester, you'll remember this in more detail. I won't go over the rationale behind this, but the important thing to note is that these equations depend on the number of atoms in the system that we're looking at, so that we have monatomic, diatomic, and we distinguish between linear polyatomics like carbon dioxide, which has 3 atoms in a linear arrangement, or nonlinear polyatomics like water, which has 3 atoms but are arranged in a nonlinear fashion. Now, these equations correspond to an ideal gas where there are no interactions and there's no potential. So energy depends only on motion, that is kinetic energy. So the internal energy of the system is equal to the kinetic energy of the molecules. But that kinetic energy, as we noted earlier, can be distributed amongst various modes of motion, like translational motion moving through space, or within a molecule, the vibrations between of atoms and bonds, or rotations of the molecule itself. And of course there's also electronic as well. We'll see that these equations actually don't work very well when we start breaking down each of these modes of motion, but that's something that we'll talk about in more detail in the lab. Now, of course, we'll note that U corresponds to internal energy, and we'll specifically note the subscript M here, and this subscript means that we're dealing with molar values. So these represent the molar values for internal energy, in this case U, 1 mole of particles. So for a monatomic system like helium, the internal energy per mole was 3/2 RT. So the important thing to note here is that it's proportional to temperature. The internal energy is entirely proportional to temperature. The CVM term refers to heat capacity, and we'll talk a little bit more about that later on. You may remember that from general chemistry, and you may remember that from physics, but we're making a distinction here that was probably not noted in your earlier classes, and that is that the CV, and we'll note the little V subscript here, corresponds to constant volume heat capacity. And that means this is a heat capacity for the system that occurs when a process being carried out is occurring under conditions of constant volume. That is, the volume doesn't change. That's to contrast with CPM here, which is the constant pressure heat capacity, which, as you might guess, is used when a process is carried out under conditions of constant pressure. We'll discuss the difference between these two in more detail in a later slide. Alright, so let's look at heat and the heat transfer that occurs for an isothermal change. We're going to ask what the value of Q would be. So we go back to our fundamental equation here. du is equal to dq plus dw in differential form. And of course, rearranging that just simply gives us dq is equal to du minus dw. For an ideal gas, of course, which has no interactions and no potential energy, we'll note from the previous slide on the equal partition theorem that du is proportional to dt, and specifically because this is isothermal, that means no temperature change, dt is equal to 0, and that then means that du for an isothermal process for an ideal gas, and I can't emphasize that enough, this is for an ideal gas, an isothermal process has du being equal to 0. This is not necessarily true for real gas behavior. We'll talk about that later in the semester. So since du is equal to 0, then we go back to our equation here, and we'll find that under conditions of an isothermal process, that dq, the heat transferred, is equal to negative dw. Alright, now we'll look at constant volume process and what dq would be equal to under those circumstances. First, we'll note, of course, as we said in the previous video, that when the volume is held constant, that the work done is equal to 0, and that means that du is equal to dq. We'll use a little subscript here of V to indicate that we're talking about a constant volume process. And so you may recall from your physics class and general chemistry class that for a process where there's a temperature change, the heat transfer is equal to the heat capacity times the change in temperature. So dq is equal to cv dt. And again, cv is the constant volume heat capacity because this is a constant volume process. As you might suspect, the reason we do this is because the constant volume heat capacity is in fact different from the constant pressure heat capacity. And in general, we'll note that the constant pressure heat capacity is greater than the constant volume heat capacity. Why is this? Well, if we look at a constant volume process, because there is no work done in a constant volume process, all of the energy in the system that goes into the system is going to go in as heat and is going to result in a temperature change. So for a constant volume process, the temperature change that occurs would be greater than would be the case for a constant pressure process. In a constant pressure process, we're going to see a situation where, because the pressure is constant, the volume will change, and if the volume is changing, the work is occurring. So because work occurs due to the volume change, we're going to note that there's less energy available for the temperature change. So some of the energy that's put into the system goes into work, some goes into a temperature change. In the case of a constant volume process, all the energy that goes into the system will go toward the temperature change. So because in a constant pressure process less energy goes into the temperature change, that means the temperature change will be less than would be the case for a constant volume process. And if the temperature change is less, the heat capacity is higher. So again, we're going to note that the heat capacity for a constant pressure process is greater than that for a constant volume process. This is most significant for gases. We'll find the difference between constant pressure heat capacity and constant volume heat capacity is in fact very, very small in the case of liquids and solids. And we'll be looking at expressions that allow us to calculate that difference a little bit later on in the semester. We'll also note that when you go to thermodynamic tables, for example, in your book, you're more likely to find the constant pressure heat capacity value than the constant volume heat capacity value. And that's because most of the time, if you think about it, when you're carrying out an experiment in the lab, frequently the conditions are constant pressure conditions. So, for example, if you're doing some solution work in the lab and the beaker's open, then clearly it's a constant pressure kind of situation. We'll actually do an experiment in the PChem lab over the next few weeks, bomb calorimetry, where the process is a constant volume process, and we'll certainly talk about that later on. So our expression here for du being equal to cv dt clearly is correct for a constant volume process, but it turns out that for an ideal gas it is correct and is true regardless of whether it's a constant volume process or not. So even if it's a constant pressure process, for an ideal gas we can calculate the internal energy change by using the constant volume heat capacity. Again, let me reiterate, du being equal to cvt is always true for an ideal gas, regardless of whether it's a constant volume process or not. And so that means we can rearrange this equation, and we've got du dt is equal to cv, and in particular we have an expression here that shows the definition of the constant volume heat capacity in terms of internal energy changes. For some of you, this notation may look a little bit different than a typical derivative, but we'll note that the subscript v simply indicates that we're talking about a constant volume process, and the slight distinction difference in the derivative itself, rather than full d's, we refer to as a partial derivative. And partial derivatives will be used throughout the semester Again, for those of you who are unaware, we'll use partial derivatives anytime we have a system where there's more than one variable. In the case here, in the thermodynamic systems, we have three variables: temperature, pressure, and volume. But two of those are independent variables. That means if we know one of the variables, if we know two of the variables, we can calculate the other. For example, if we know temperature and volume, we can use the gas law to calculate pressure. So we have two independent variables here, and this derivative simply shows that we're taking the derivative with respect to temperature while holding the other variable, volume, constant. When we get to the next chapter, we'll talk about partial derivatives and their applications and the mathematical expressions in more detail. It's also, just going back to that, important to note that when it comes to actual taking the derivatives of mathematics, the rules for differentiation are the same as those you learned for single variable systems. Now, let's talk about enthalpy. We haven't talked about that yet from general chemistry and your other classes. You used enthalpy extensively when doing thermodynamic calculations, and I'm sure you always referred to enthalpy and heat interchangeably, so delta H for a process was equal to Q. Well, that's not entirely correct. The definition of enthalpy, H, is given here as being equal to U, internal energy, plus the pressure volume product. Now, that may seem kind of arbitrary, but you'll see in a second why we define it that particular way. If we use a differential form, if we look at both sides of the equation, we can have dH equal to du plus dPV, and we'll make the substitution that du is equal to dq plus dw. So let me actually just write that here just to make that clear in this circumstance, that du equals dq plus dw, and we make that substitution in order to write this expression. And then we'll also note that dPV, we use the simple product rule that you learned in calculus, or dPV is equal to pdV plus dP in that expression. So we now have a differential form for enthalpy, and we're going to look specifically at the condition of constant pressure. Now, under conditions of constant pressure, that means dP is equal to 0. So that means the last term in this equation goes to 0. We can eliminate that. So we're left with this expression where we eliminated that. And then we're also going to take dW and simply use our expression for dW as being equal to negative PdV. So now we have the situation that dH is equal to dQ minus PdV plus PdV. And again, this also, it's important to note, would be rigorously true only for a reversible process when the internal pressure is equal to the external pressure. And of course, we'll also add the subscript here for dQp just to indicate that we're talking specifically about a constant pressure process. Alright, so of course these last two terms cancel each other out, and when we do that, we see that under conditions of constant pressure, dH is equal to dQ. And then, of course, associating that with heat capacity, we'll note that dQ is equal to Cp, where again, because this is a constant pressure process, the heat capacity that we're used here is the constant pressure heat capacity. And again, so we see that under conditions of constant pressure, dH is equal to dQ. But that's only under conditions of constant pressure. The equivalence of enthalpy change with heat transfer is true when the pressure is constant, but if it's not a constant pressure process, it is important to note that dH is not equal to dQ. In fact, you may recall that for a constant volume process, its du is equal to dQ. So whether we use enthalpy or internal energy in our calculations will depend on the nature of the process itself. And again, we have the distinction between the constant volume and the constant pressure heat capacities. It's also important to note that just like the case for du being equal to CV dt being always true for an ideal gas, dH being equal to Cp dt is always true for an ideal gas. So it doesn't matter whether it's a constant pressure process or not, dH is equal to Cp dt under all conditions for an ideal gas. If you're talking about a real gas, not so much. But for an ideal gas, that would be true. And again, just as we wrote in the differential expression in terms of partial derivatives for the constant volume heat capacity, we now have a definition of the constant pressure heat capacity in terms of the partial derivative of enthalpy with respect to temperature. Again, here we're dealing with conditions of constant pressure. So we'll note that distinction in comparison between the constant pressure and constant volume heat capacities. And again, later on, we'll look at derived specific expressions that allow us to calculate that difference for gases, liquids, and solids. And again, just a reminder, Cp is going to be greater than Cv. The distinction is most different in the case of gases. And in the case of an ideal gas, we'll note that Cp is equal to Cv plus N times R, N being the number of moles, or if we want to deal with molar quantities, then Cpm is equal to Cvm plus R. So this ends our discussion and introduction to heat associated with internal energy changes and introducing the new thermodynamic quantity enthalpy, which is a function of state, just as is the case of internal energy. In our next video, we'll talk about the basics of adiabatic processes involving ideal gases.